this set of notes is on limits at infinity. So we've done limits going when x is approaching a certain number. So this is when x is approaching either infinity or negative infinity. So let's look at when we have a certain graph. So our first graph, f of x, if we sketch our graphs here, we have 2x plus 1 over x minus 1. Now we have some asymptotes, and our asymptotes on this one, we have a vertical asymptote at x equals 1. And we have a horizontal asymptote here at y equals 2. Now, if you remember how to get these asymptotes, you get your vertical asymptote by setting your denominator equal to 0. So if we take x minus 1, set it equal to 0, we'd get x equals 1. You get your horizontal asymptotes by looking at your powers of the top and bottom. So, for example, you can always use Desmos as well and get an idea of where your asymptotes are. But also, if we were to look at our powers here are even. And so if you look at the leading coefficients here, we have a 2 and there's a 1 here. So our asymptote would be 2 over 1. And so that's where the 2 comes from. But like I said, you could also plug these in on Desmos to be able to get that. But that's just a quick review from Math 3. And so these graphs, our rational function graphs, are going to look like this. Now, 1 over x, so again, if you set x equal to 0, well, just x equals 0. So we have an asymptote, a vertical asymptote here at x equals 0. Now, when your power on top is smaller than the power on the bottom, then you have a horizontal asymptote at y equals 0. And so our graph is going to look like this. All right, and for our next graph, for the bottom, if you set x plus 1 equal to 0, we'll get negative 1. And then this one, because of the x squared, we actually have a like a diagonal asymptote on this one. So this is y equals x minus 1. And our graph is going to look like this. Okay, so this is what our graphs look like. So now what we're going to do is we are just going to look at the graphs and get an idea of what our limit is approaching. So as x approaches infinity, well, that's as x goes to the right. What is the y doing? So if I look at this direction here, well, my y is approaching the value of 2. Now, if I go to the left, so for part B, as x approaches negative infinity, well, again, if I'm going this way on my graph, my y value is still approaching 2. Okay, so on C, now I'm looking at the next graph. I'm looking at the graph of g of x. So as x approaches infinity, my y value is getting close to 0. And for part D, as the as x approaches negative infinity, so as I go to the left, my y value, I'm still approaching 0 because I'm getting close to those asymptotes. All right, so on E, I'm looking at the graph of h of x. As x approaches infinity, well, as x approaches infinity, as I move to the right, my y value is increasing. It's going up, okay? It's not approaching a certain number. It is increasing. It's going up. It's continuously growing. So I would say positive infinity. And then as my limit approaches for part F is it's going down, or as it approaches negative infinity, my y value is decreasing. So I would say negative infinity for that one. Okay, so now let's look when we have some functions here. So finding limits involving infinity, and we have some certain theorems. So if you have a number on top, so if C is a real number and R is a positive rational number, if you're going towards infinity or if you're going towards negative infinity, your limit is going to approach 0, okay? So you just kind of imagine, like, if you have any number on top, C could be any number, imagine plugging in infinity on the bottom, okay? So imagine if you have a number and you're plugging in a really big number on the bottom. The bigger number you plug in on the bottom, the smaller that number is going to be. So if you divide a number by a really big number, it's getting closer and closer to 0. So that's why that is approaching 0. Now, even if it's a negative, so even if it's negative infinity, you're getting really close to, you're still getting close to 0. So think of it as negative 0.00001 or whatever that may be, okay? So even if it's a negative infinity, we're still getting close to 0, okay? So C is just a number. It can be any number, okay? But the bigger number it is on the bottom, that's why it's approaching 0. Now, we have some other limits on the bottom. We have some rules for powers, okay? So rule number 1, if your power on top is smaller, it's going to approach 0. So kind of the same rule that we looked at before. The power on top is smaller, it's going to approach 0. So then on number 2, if your powers are the same, you look at your coefficients right here, and then it's just going to be C over D, or whatever those numbers are. Now on number 3, if your power on top is bigger, then you plug in a large value for x to determine if it is positive infinity or negative infinity. So we'll see if it turns out to be positive or negative for that number. And that one may make a little more sense when we actually do that problem. Okay, so for A, we just have a number on top and x to the third on the bottom. So that's going to approach 0. So again, think if you were to plug in infinity for x cubed, so like infinity cubed, really, really huge number, 2 over a really, really huge number. It's going to be a tiny, tiny decimal. That's going to approach 0. Okay, for part B, again, you have a number over x cubed. It's approaching negative infinity, but again, that's going to equal 0 because it's 2 over a really huge number. Even though it's negative infinity, even though, like, if you think of it, plugging in negative infinity, it's still going to be approaching 0. Now, if you have just a number, you can't really plug in infinity for 7, your limit is going to approach 7. So if you ever have just a number, it's going to approach that number. All right, on D. So we have 7 here. So kind of think, if we plug in a 7, that's just a 7. 2 over x cubed, well, that would be a 0 right there because 2 over a really huge number is going to approach 0. And then 7 plus 0 comes out to be 7. So that's how you do a problem like that. Okay, on E. So this is looking more like that little second section there where we're looking at those powers. So take your highest power. So our highest power on E is the x squared here. Highest power on the bottom is an x squared. So these involve the same powers. So you take that leading coefficient on top, which was a 3. There was a 3 with the x squared. Leading coefficient with the bottom x squared, which is a 2. And so our limit approaches 3 over 2. On F, so on this one, our highest power is on the bottom. It's an x squared. So again, we're just worried about where the highest power is. So if you plug in, so again, you kind of think of it as if you're plugging in infinity. 3 times infinity is not going to be as big as if you square an infinity. If you square an infinity, that's going to be way bigger, and you have a way bigger number on the bottom, which gives you a really small fraction. Think of it like that. so it's going to approach 0. Okay, on G. So now we have a higher power on the top. So this is where we plug in your a large value to determine if it's a positive or a negative. So if you plug in a positive infinity here, well, positive infinity squared is going to be a positive number. If we plug in a positive here, it is also going to be a positive. Well, a positive divided by a positive is positive, so it's going to approach positive infinity. On our second one, well, the bottom is a bigger power, so that means we are going to approach 0. All right, when we're involving sine or cosine, we have a property that actually says that the limit as x approaches, and it can be positive or negative infinity, that of the sine of x over x equals 0. Now, if we have numbers thrown in there, there's a rule that says like we have to multiply to get the same on top as the same on the bottom, but I'm not going to go through all that. So just know that if it involves sine and cosine, that it's going to be 0, and it doesn't matter if it's positive or negative. So on J, this one is also going to be 0. Now, that's not to be confused if it approaches 0, okay? If the limit approaches 0 and we have sine of x over x, that is not going to be 0. That actually equals 1, so be careful with that. Okay, so this is only 0 if it equals, or if your limit's approaching infinity. Okay, so on this one, on K, our limit is approaching negative infinity, or x is approaching negative infinity. Our power on top is bigger. So again, we plug in negative infinity. Well, if we cube a negative, negative cubed turns out to be negative because an odd power is negative. And on the bottom, if you square a negative, it's a positive. So negative divided by a positive is a negative. So this will be negative infinity, and that's all because of what our limit is approaching. That's why we're plugging in a negative here. Okay, on L, so on this one, notice on this one, our highest power here is a square. Our highest power here is also a square. So we take the 4, we take the 2 on the bottom, and that simplifies down to a 2. Okay, and so this is all a shortcut. So real quick, I just want to show you, oh wait, we have one more. Almost missed that one. So on this one, a 1/3 times x. So if you think of 1/3 times infinity, well, that's just going to be infinity. And then 5 over x cubed, well, that's a number over, so that's like our top rule there. Well, that's just a 0. Well, infinity plus 0 is going to give us infinity. Okay, so like I was saying before, this is all shortcuts. The real method for evaluating limits is what you would do is you would take the largest power in the denominator and you would divide all terms. Okay, and this is why we use the shortcut, because this is a little bit longer. So like for example, if we take example H, okay, so if we look at H, my largest power is an x cubed. So if I did 1 divided by x cubed minus 2x over x cubed, and then x cubed divided by x cubed minus 2 over x cubed. Well, 1 over x cubed, if I use that same rule, 1 over x cubed is going to go to 0. And then 2x over x cubed, if I'm doing infinity there, that's going to go to 0. And then x cubed divided by x cubed is going to be 1. And then 2 over x cubed, that's going to also approach 0. So I have 0 over 1, which comes out to be 0. Okay, so we do all those steps to get to 0. And then if I even look at L, where I get a whole number of 2, or I get an infinite answer, or a finite answer of 2, so my highest power on the bottom there is x squared. So if I do 1 divided by x squared minus 3x over x squared plus 4x squared over x squared, and then I have 2x squared over x squared plus 3x over x squared plus 5 over x squared. Well, here, 1 over x squared, that would be a 0. 3x over x squared, that would be a 0. 4x squared over x squared reduces to 4. 2x squared over x squared is 2. 3x over x squared, that is a 0. And then 5 over x squared is a 0. And again, that reduces to 4 over 2, which gives me a 2. So we have our real method. This is where our limits, getting our limits comes from, but that's why we use our shortcut.